Okay, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. So now I'm inshallah, but whatever it is, let's have our Webex conference for today. Okay, so the thing is I don't see any of your chatting in here, so you just please on your microphone if you like to ask any question. Is there anyone around? Okay, whatever it is, today we are going to talk about access carriers in semiconductor, basically about the optical absorption and luminescence. Okay, let's say we have a spectacle and at night we can see that there's some light that comes out from our spectacles, like the one shown here, even though there's no light around. It's in the dark, but you are able to see some light that coming out from it. Basically, I mean, there are also new t-shirts that glow in the dark. So basically what you are going to learn today is something about how it happened. Okay, if you look at this diagram, I mean, let's see the tagline. Making heat and one red out of one blue. I mean, it's so simple, only a sentence, but it really is illustrate what it means by optical absorption and luminescence. If you see here, this is a Venn diagram of a material where the material absorbs blue light, photon in the form of blue light. But the thing is, this material has a band gap that will give out photon in red in color. So whenever it absorbs, let's say this blue photon, since its band gap is only around red photon, so some of the energy that's being absorbed is going to be lost as heat, and then only recombination occurs from the from the conduction band edge to the valence band edge. This one graphically been shown here, photon being absorbed, where it goes to the higher energy level, and then it undergoes scattering, where it gives out heat, and lastly it jumps back to the valence band, and what comes out is the red photon or red light. So making heat is what happened during the scattering. If you can recall your old TV, which we used before, whenever we used the television for some time and it gets hot, so this is due to this electrons in the TV goes down a lot of energy by scattering in the screen in front of the TV. So some energy is lost, and then we have our photon that is radiated out. So basically what we are going to learn today is explain the origin of these excess carriers in semiconductors, and also explain the relationship between the intensity and the transmitted incident light. And by knowing this relationship between the intensity of the transmitted and incident light, you are able to calculate how much of the light has been absorbed, and also how much of it photon that's going to be given out, that's going to give you this luminescence. So basically, we are going to start with knowing where is the origin, and then lastly, calculating the recombination for these carriers, which will give us how much photon per second and how much of it is going to be absorbed, and also how much of it is going to be lost as heat. Okay, so hopefully after this Webex conference, when you see a t-shirt that glows in the dark, you would know how it works, and basically you also know how many of the photons is going to be emitted per second if you know how much power that's in the light that's incident upon it, and also what kind of material that is made of that gives the luminescence pattern. Okay, let's start with explain the origin of excess carriers in semiconductor. Of course, whenever we talk about semiconductor, whether it's luminescence or what, it's best that we start with the energy band diagram. Let's say we have an excitation where the energy should be more than the E gap. Why? And the excitation, it can occur by using four methods, whether you can have light incident on your material, or you can also have high energy particle bombardment, and also as usual in our case before, we use electricity, the one in our old televisions, and also by using heat. So there are four methods for us to have this excitation. Basically, as I said just now, the energy that's going to be absorbed, H nu, must be greater than the E gap. Why is it so? So if we look here, absorption, alpha is the absorption coefficient, and this one is the energy. You can see here that whenever the energy is around E gap, only absorption starts to increase. So that's why the incident energy should be greater or equal to the E gap, so that more is going to be absorbed. Okay, if we look here again at this diagram, this on the x-axis represent the E gap. Different materials have different energy band gap. If we look here, germanium, the E gap corresponds to the infrared region. So does silicon and also gallium arsenide. But if we look here at gallium phosphide, it falls upon the visible region where it's about 2 point something, about 2.2 to 2.3 EV, where it gives around between yellowish green. And for zinc sulfide, it gives around ultraviolet light. So you can see that different materials have different E gaps, and recombination electron from the valence band, from the conduction band to the valence band, if you look here, will give out photons that correspond to the E gap. Okay, during absorption, you can get extra electron hole pairs, where these electron hole pairs are being the excess carriers. Because it's going to be excited by light or high energy or electricity or by heat. So we have these excess carriers in the semiconductor. And then, since it has more energy than the E gap, so part of it is going to be lost in the lattice scattering where it's actually going to heat up the material, the semiconductor, and the rest, when it jumps down back to the valence band, so during recombination, and what comes out is our photon. Soon you will be able to calculate how many photons that's going to be given out, provided we know how much is the power of the incident energy and also the E gap of the material. Okay, so basically it is all about where does the about how the excitation method, and the condition of it, because we know that at around E gap only, absorption does increase. Absorption does increase, so that's why it should be more than an E gap. And then after that, formation of the electron hole pairs, where the electron hole pairs are being the excess carriers, where the electrons will undergo lattice scattering, where it gives out heat to the material, and then when after it recombines back with holes here, then you have your radiated photons, where normally since it's a band-to-band recombination, so your energy is equal to your E gap. Basically, for in a direct semiconductor, then you get the photon that corresponds to the E gap. Okay, do you have any questions? Because I'm not able to see your chat lines here. I'm not sure why. But the thing is, if you have any questions, just on your microphone. And just say out your question. Okay, since there's no question, let us try out this problems and see. Let me see. I can almost check. Let me see. Okay. Let me see if there is anyone around. Any participants? Oh, that's Farah, there's Muhammad Khairi, there's Nasaruddin. Okay, I'm on the chat line. If you would like to ask any question, do you understand what I've been trying to tell you, to inform you just now? Farah, is it okay with you? Khairi, do you have any question that you would like to ask me? What about Nasaruddin? No question? Okay, let's move on then. If you are given two materials to choose, as phosphor for TB screen, which one would you select? Zinc sulfide or cadmium selenide? Explain your answer. So, how are we going to solve this problem? Let's see, we have this as a guide to help us make our decision. Okay, so would you select zinc selenide and zinc sulfide or cadmium selenide? Zinc sulfide or cadmium selenide? So the thing is, whenever, for our old PD, but see, this is a very good example, so let's just go for it. Yeah, phosphor for our TV screen. Since we know that for our TV screen, we need to have it to be multicolored, isn't it? So if we choose cadmium selenide, then we have only a TV screen that's only having red color. But of course, it won't be interesting, isn't it? Because everything is going to be reddish. So the best choice is to have to choose zinc selenide, isn't it? Because zinc selenide, even though it's going to give up ultraviolet light, but the thing is, it's possible for us to introduce trap in it so that we are able to produce, let's say this is the conduction band H, our energy band gap. Yes. If band-to-band transition, then we can have our UV line. But the thing is, if we introduce trap in between, let's say we have a trap here, so the electron will go down here. Then when it goes down to the valence band, it will give out red light. So this one will lose as heat. So let's say we would like to have another color green, let's say. So that's I didn't see my I didn't have anything green. Let's say we have blue. Okay, blue. We can have introduced a trap here, put material in our zinc sulfide. Then when it goes down, so it will give us a blue light. So you can see we can tailor-make our zinc selenide material, the zinc sulfide material, in such a way that we are able to get different colors. But since if cadmium selenide it only gives red, so red, the energy band gap is small. So band-to-band transition gives red color. But if we introduce any any trap in between, the color that comes out will be around infrared. The energy will be infrared, which you won't be able to see any color for cadmium selenide. So this one not possible because for the energy difference between this one and this one is small, which corresponds to infrared. But for ultraviolet, since the gap is big, so you are able to tailor-make according to what you want. Okay, is there any question so far, Farah? Or Khairi? Or Nasaruddin? Okay, if there's no question, let's look at another situation. If the band gap of ternary alloy, gallium and arsenic phosphide varies with composition from gallium arsenide, varies from gallium arsenide to gallium phosphide. Here. One wavelength range of colors is covered. Okay, so if you look here, gallium arsenide is around infrared and gallium phosphide is around, it's between yellow and green, so yellow. So the color that's going to be covered will be IR, red, and yellow. So you can vary the amount, the concentration of gallium, arsenic, and phosphide in order for you to have the different colors, red or yellow, or you want to have concentrate on infrared. Okay, so basically what you see here today is the E-gap plays a very important role in us getting the color or the energy that is really going to be radiated out during recommunication. Okay? Oh, great, Heidi. So I've got your message here. Okay, so far okay. It's quite simple, isn't it? Okay, now let's go to the nitty-gritty, the very important part of it. That one is how E-gap mempengaruhi, how E-gap controls or influence the absorption of the excitation energy. Okay, let's move on. Okay, let's explain the relationship between the intensity of the transmitted and incident light. Because by knowing this one, then only we are possible to calculate how much energy is going to be absorbed. Okay, so let's move on. Okay, let's say we have a monochromatometer that gives out a light with intensity I sub 0, and then our sample, where our sample has a length L, and our sample absorbs a certain amount of the energy, and the rest of it is going to be transmitted, I sub K. But the thing is, what is the relationship between our incident intensity and also our transmitted intensity? Okay. Okay, we start off with the degradation of intensity because we know that part of it has been absorbed by our sample. Okay, degradation intensity is the differentiation of the intensity over X. So, okay, the degradation of the intensity as a function of X. So, you can see that is proportional to I, where since if you like to put the equal sign, we have to put a constant. So our constant is the absorption coefficient, which is essentially what I've showed you just now. Yeah, the absorption coefficient. Okay, next. What is the solution to this degradation of intensity equation? So the solution is the solution is I transmitted is equal to the incident intensity multiplied by e to the power of negative alpha x, the length, the width. So we can see that there is a decrease in the intensity after some of it has been absorbed by the sample. So in our case, the length transverse is L. So we can safely put that. So X is equals to L, then I is equals to Let me just move this down. So I sub K is equal to the intensity of the transmitted light is equal to the incident multiplied with e to the power, a factor of e to the power of negative alpha L. And shortly we are going to use this equation in order to find how much of the incident energy has been absorbed by our sample. Okay, let's move on and try to use it in a real situation. Okay, I hope all of you has put it inside your mind that the intensity of the transmitted light is equal to the intensity of the incident multiplied by E exponential E negative alpha L. Okay, jot down this equation somewhere because you are going to use it shortly. Okay. Okay, next. Let's solve the optical absorption and luminescence problems. Okay, let's have this this question. A 0.46 micrometer thick sample. So this is going to be our L, isn't it? So this sample of gallium arsenide is illuminated with a monochromatic light having an energy of 2 eV and energy 2 eV and power of 10 milliwatt. The absorption coefficient at this wavelength of light is 5 times 10 to the power of 4 per centimeter. Then the question is how much energy per second is absorbed by the sample. Okay. So now we know what's the power and we know what is the absorption coefficient. Of course, it's possible for us to calculate the energy per absorbed per second because you know already what is the incident and of course the transmitted relationship between the transmitted and incident. So naturally it's possible for you to find the energy per energy absorbed per second. So let's have it graphically. So energy absorbed per second. We know that that's our incident, excitation energy, the intensity of the incident light, and the intensity of the transmitted light. And we know that it has a power of 10 milliwatt. But the thing is, what is the relationship between power and intensity? Power, intensity is equal to power over area. And we know that power is essentially energy over time. So, what about the area? Area is not being given anywhere, isn't it? Well, to make matter easy, we just keep our area constant at 1 meter squared. Easy, isn't it? Make our life simple. Don't complicate life, everyone. Okay, so now, to get the E absorbed, is essentially our incident energy, intensity minus our transmitted intensity. And we know what is our transmitted intensity, isn't it? So, oops. Okay. Our incident is 10 milliwatt, because we keep the area 1 meter per second, isn't it? So we can just use our 10 milliwatt straight away, minus our intensity transmitted. But we know the relationship between I sub t and I sub 0, isn't it? So we need to find it, but we know that equation which I've showed you just now, and I sub 0 is 10 milliwatt, and then our alpha is being given already here, and our L is the thickness, 0.46 micrometer. So you just put it in. But the thing is, our absorption is per cm. So basically our L should be changed from micrometer to cm. So we have that. Yeah. Convert micrometer to cm so that you can cancel it, because this is cm and this is per cm, then you will be cancelled. So just plain mathematics. So you can get that your I transmitted so it equals to 1 milliwatt. So 10 milliwatt minus 1 milliwatt. So we get the amount of energy absorbed is equals to 9 milliwatt. See how wonderful is it, isn't it? So now you are able to know how much energy is being absorbed by the sample. If you know what is the thickness and what is the amount of power, then you are able to know. Isn't it? Such beauty. And now let's go one step further. Let's calculate how many photons are going to be available when this excitation happens. Isn't it great? I mean, by knowing the thickness, by knowing how much energy that the monochromatic light has, and also how much power. Let's say we use the 10 milliwatt laser, and then we know the energy that it has is 2 eV, and then the absorption coefficient of this gallium arsenide for this light at this wavelength is 5 times 10^4, and we know the thickness. And you can calculate how much energy has been absorbed per second. And now let's go one step further to know how many photons are being given out per second. Okay. All right. So assuming perfect quantum efficiency, one emitted photon for one photon absorbed, how many photons per second will be given out from the recombination event? So how are you going to go about getting the number of photons per second? We know already how much of energy has been absorbed, isn't it? But the thing is, we know how much has been absorbed. Okay, let's go. Let's have it. Okay, we know how much that has been absorbed to, no, we know what is the incident energy. And we know how much of it has been absorbed. We have calculated just now. But the thing is, before it recombines to give out a photon of energy 1.43 eV, because our sample is gallium arsenide, isn't it? Gallium arsenide, the band gap is 1.43 eV. We need to know how much heat is given out. Then only we can know how much of it, how many photons is given out per second. So we know incident, and we know how much energy has been absorbed per second, but we need to find how much of it is lost as heat before we will be able to calculate how many photons per second. Okay. Okay. Photon per second is equals to energy per second available for recombination divided by the band gap energy. But the thing is, what is the energy per second available for recombination? So what is it? So it's essentially the energy that's being absorbed, which we know, which we have calculated just now, but we need to find, that one we know already, we have calculated it just now, but what about the EV? We have yet to know, isn't it? So, how do we calculate the amount of energy that's been lost as heat? Now you have to find. So, heat over time is the fraction of the incident photon energy converted to heat multiplied by the absorbed energy per second. Okay. Fraction of incident photon energy converted to heat is essentially the incident photon energy minus the E gap divided by the incident photon energy. And each fraction, how much of it has been absorbed just now? We absorb is 9 milliwatt. Then we have the amount of heat that has been, the amount of energy that has been lost as heat due to the lattice scattering. So we have it here now. Because why do we use fraction of incident energy photon converted to heat? Why we use this fraction? Because we know that the excess of, because 1.43 is the band gap. So the excess between the incident photon energy and the band gap is going to be lost as heat. We divide by 2 so that we can have it as a fraction, because we knew that the amount of energy that has been absorbed is 9 milliwatt. We would like to know how much of the 9 milliwatt that has been absorbed is lost as heat. So we have it here now. So we just plug in everything. So we have now that we absorb 9 milliwatt, and then the amount of energy that has been lost per second. Then 1.43 is the E gap of our gallium arsenide, and of course we change it back to the SI unit, so we are able to get 2.81 times 10 to the about 2 times 10 to the power of 16 photons per second, which is a high number. Okay. So, is there any question as for now? Farah, Khairi, and also Nasaruddin, do you have any question? No? So, it's only you for this class today? Is there any question? No question at all? Okay. What can I say? Do you want to have any assignment? Anyone? Quiet. So we have our own assignment. Perhaps tonight I'll open up for your assignment. Quiz. I'll open tomorrow from 9 to 10. So tomorrow from 9 to 10 a.m. in the morning, I will open up your quiz. And tonight, I'll open up for assignment for this Webex 3, which I'm going to give you 2 weeks to do it. Okay, is that okay with all of you? Oh, everything seems to be quiet. So I'll open up tomorrow quiz, a Webex 3 quiz from 9 to 10 tomorrow morning, and assignment Webex 3 tonight, which for the assignment I will give you 2 weeks, and for the Webex is only open between 9 and 10 a.m. tomorrow morning. Okay? Since there's no response at all, so I would like to thank all of you, Farah, Khairi, and also Nasaruddin, for being present during this Webex conference. And I hope to see you during the intensive course, which we will work through the student workbook that I have uploaded in your portal. Okay, thank you everyone. See you during the intensive course then. Okay, goodbye.